Hello everyone, welcome back. My name is Mr. Cobalt, and in this video I'm going to be talking about VSEPR theory and how to use VSEPR theory to predict the shape of larger molecules. And really all it comes down to is making sure you know what shape is around each of the central atoms. So when we talk about larger molecules, we're usually talking about molecules that have more than one central atom. So it's really easy because all you really need to do is just focus on one central atom at a time, figure out what the shape or geometry is around that particular central atom, and then move to the next one until you've done it for all the central atoms. So that's what I'm going to do here. I'm going to go over a couple of example problems and show you how it's done. So the first thing you need to do is write your Lewis dot structure. So again, if you're not familiar with Lewis dot structures, or if you need to brush up on that or need to review, please see my other videos where I talk about Lewis dot structures and how to create your Lewis dot structures. So here I have a couple of examples. I've got the molecule, the molecular formula here, and I wrote out the Lewis dot structure here. So let me just move my, let's see here. Okay, that's better, I guess. Okay, so one thing when you're given a formula, again, a lot of times when they draw organic molecules in their formulas, they kind of break it up into the different sections of the molecule. And that when they write it in that form, it's easy to figure out what your skeletal structure is. Because then it tells you CH3 goes together, so you got your CH3, and then you've got your OH part, and then you've got your OH there. So if you remember, OH is a good giveaway, a dead giveaway for a molecule to be identified as an alcohol. So when you have an OH group in your molecule, this is not hydroxide ions, this is not ionic substances, this is molecules. So if you've got an OH group in your organic molecule, it's an alcohol. So here's our molecule. This is methanol. And so we have two central atoms here. We have the carbon and we have the oxygen. So let's take the carbon at first. So we're going to identify the molecular geometries, because that's the shape of the molecule, is the molecular geometries. So for the carbon, the total number of groups is going to give you the electron geometry. So what are the total number of groups? We have 1, 2, 3 bonding groups, 4 bonding groups, and we have no lone pairs. So the total number of electron groups is 4. So for the electron geometry, that would be tetrahedral. Now for the molecular geometry, that's going to be different if you have lone pairs, but we don't have any lone pairs. So in this case, the molecular geometry is identical to the electron geometry. So the molecular geometry for the carbon, the molecular geometry for this carbon is tetrahedral. Okay. So that's the molecular geometry. So the shape of the molecule around the carbon is tetrahedral. What about the oxygen here? So here we have, again, if you count the total number of groups, 2 bonding, 2 lone pair, the total is 4. So again, the electron geometry is going to be tetrahedral, because electron geometry is only based on the total number of electron groups bonding and non-bonding. So the electron geometry is going to be tetrahedral. However, the molecular geometry is only based on the bonded atoms. So again, you might look at this and say, oh, it's linear. You would be wrong. So don't mistake how it's drawn as a Lewis dot structure to influence how you think about the shape around this oxygen. It's not linear. So again, if you remember, it's tetrahedral electron geometry, but 2 of those electron groups are lone pairs, so we ignore them and we look at the rest of the molecule. And the rest of the molecule here is going to be bent. So it's going to be bent here because that's what the molecular geometry is when you have two lone pairs and two bonding groups or two bonds. So here you would expect this part to be bent. So bent is the molecular geometry for the oxygen. So that's how you can determine the shape of the molecule at each of those central atoms. So what about acetic acid? So again, this is the formula for acetic acid. So you can see that the way it's written here is broken down into chunks. So CH3, CH3, CO2, CO2, and then UH. I got the H here. So this is how you draw the Lewis-Dot structure for acetic acid. So again, you're going to determine the molecular geometry for each of the central atoms. And in this case, we have 1, 2, 3 central atoms. So here, you can see that, again, we have 1, 2, 3, 4 bonds around the carbon, no lone pairs. So again, just like this one, the molecular geometry is the same as the electron geometry. So tetrahedral. So again, tetrahedral is when you have 4 total groups. The electron geometry is tetrahedral if you have 4 total groups, bonding and non-bonding. And in this case, there's no lone pairs, so the electron geometry and the molecular geometry are the same. So the molecular geometry is also tetrahedral. Now, what about this carbon? Now, we're going to count the number of total groups. We have 1 bonding group, another bonding group, and again, that double bond is only 1 bonding group. So we have a total of 3 bonding groups, no lone pairs. So again, in this case, the electron geometry is the same as the molecular geometry because we don't have lone pairs. So if you look up, or if you know, that whenever you have a total of 3 electron groups around your central atom, the electron geometry is trigonal planar. So that is the molecular geometry. So we have trigonal planar. Okay, so that's the shape around here. So the shape around this one is going to be a planar, flat part of the molecule, and it's going to be, again, if it's trigonal planar, it's going to be at about 120 degrees. Now notice this double bond here. So this is not going to be ideal because we have single bonds here and we have a double bond there. There is no resonance, so they're different bonds. So this double bond here, the electrons in here are going to have more repulsive force because you got more electrons. So these guys are going to need more space. So these 2 bonds are going to be pushed closer together. So I would say that the bond angle here and here is going to be larger than 120. The bond angle here is going to be less than 120. Here you would expect the bond angles to be about 109.5. Although you do have this large part here, so that large part could influence the bond angles here. So it may be less than 109.5. So now for our oxygen, the oxygen here has the same environment here, 2 bonds, 2 lone pairs. So again, the molecular geometry is going to be bent. But again, the molecular geometry is bent, but the electron geometry is going to be tetrahedral. So electron geometry, tetrahedral, molecular geometry, bent. And so you would expect this part of the molecule to be bent. This molecule is going to be flat with a flat part of the molecule, and this one is kind of a tetrahedral part of the molecule. And so that's how you can determine the shape of larger molecules by determining the shape of each central atom. And so that can kind of give you a visual in your mind of what this molecule should look like. I hope this was helpful. If you have any questions, put them in the comment section. Ask me questions. Tell me what you think. Is there anything you want me to go over? Also, if you like this video, share it. Hit the like button. Hit the notification button so you can get more videos from me or be notified. And, hit the subscribe button and subscribe to the channel. Thank you for joining me, and I'll see you next time.